everyone. Today we are going to start a new chapter we talk about the decision trees. So we'll spend at least 2 sessions or maybe 3 sessions on decision tree. We will also have a hands-on session probably next week. So here is the outline for today. So we describe what is decision trees and how we actually represent data in decision tree learning. And we also learn a decision tree from data. So we see some basic decision tree algorithm and how we actually select the best attributes. So these are the topics that we discuss today. So we can use decision tree for either classification or regression, but the focus in this lecture is on classification methods. So under the classification methods that we'll discuss, one of them is decision tree for classification. So first, let's start with the classification itself. So what is the classification? So the classification is a 2-step process, right? And you already see it in the slide. But just to make the class a bit more interactive, can someone let me know what the classification is? Yep.
Like after training, on inferencing, should I say that?
How about the training phase?
Okay, for the training phase, then you take labeled data and then give it to the model, and as it goes through the data and gets things right and wrong, you update the parameters of the model.
That's correct. So the first stage, so we have a data set, and so the classification is a 2-step process. In the first stage, we have our training data and we try to learn from this training data. So our learning algorithm tries to learn from the training data to build a classification model, sometimes also called as classifier. And now the second stage, we use this classifier and our test data, so is another subset of our data which is independent from the training set. Otherwise, our evaluation is not fair. So we use that training set and a classifier, apply that on a test set to see how our model performs. So if the accuracy is acceptable, then we can use that classifier to predict or classify the new instances of data that we get, right? So we have 2 sets of data here, training set, which we use in the first stage, and we have the test set, which we use in the second stage. So here you can see an example. For example, we have, let's say, a data in the form of a table. We have name, age, income. These are our features or attributes. And then the loan decision is our target variable, or is actually what we want to predict, right? So now we want to see if a customer, when we want to decide, when let's say a bank wants to decide to give a loan to someone or not, so they may consider several factors, such as, for example, their age, their income, to decide whether that person is safe for the loan decision or is risky. And so here's an example of the training data. We feed the training data. Actually, the learning algorithm uses training data. And to build the model. Now, what you see here for the classifier or the model is in the form of some rules, but it could be in other forms. So here this is just an example. So the first stage here, which is the learning, in this stage our training data are analyzed by our classification algorithm to build a classifier. And so here, what is the class label here? So class label is always that feature or that column that we want to predict. So what are the class labels? Right, so we want to predict the loan decision. So the loan decision is our class label. So whenever, for the rest of this lecture, whenever I talk about the class label, I mean that feature or that attribute, that column that we want to predict. And the other columns are just used to as a source of information to train our model. So now, as you can see here, our learned model or our classifier is represented in the form of classification rules. So for the classification rules here, for example, if age is youth, then how would be the loan decision? So you can see for the rows that the age is youth, for the data instances that the age is youth, how would be the loan decision? Risky. What about middle-aged? Could be either safe or risky depending on the income, right? That is how we later see how we actually build the decision tree from the data. Or for example, when we have to reach the leaf in our trees, when we can't further branch out our trees, is when you actually, all the instances in that tuple, they all belong to, all instances belong to the same class label. So for example, now for the youth, all instances belong to the class label risky. So when we later we learn that when we want to create our tree, that is where we reach the leaf, or we don't go further. But for example, for the middle-aged, because it could be either risky or safe, and it depends on another condition of checking the income, so that's where we have to continue expanding the tree. And so far, our learning algorithm used that training data to build a classifier or build a model. And now in the second stage, we want to evaluate that model. We want to see how good it performs. So why we cannot, we use it actually on a test data that you see here. So here is just an example of a test data. Why do we use test data? Why we cannot evaluate our model on the same training set? So for example, let's say we have a data set with 100 rows, and why should we split it to train and test? Why can't we just evaluate the model on the same data? I'm sorry?
If you only evaluate using the training set, then you only know it works for the training set. You don't know it works for the rest of it.
Yeah, exactly. So it's gonna kind of get biased, and it overfit. It learns the data very well that we don't know that whether it is going to perform well on other unseen data, right? And so we use the test data to estimate the accuracy of our classifier or our classification model. In this case, it is represented in the terms of classification rules that we saw in the previous slide. Now, for example, if we see, so if our accuracy is acceptable, we said we can use that model to predict the class label for future unseen data, right? Now, let's say that future unseen data is that. So, for example, we have a tuple. John Henry is the name, age is middle-aged, income is low, and what would be the loan decision prediction using our classifier?
Risky.
Why?
Because Sylvia is middle-aged and her income is low, so
Yeah, so you look at the features. So it is middle-aged. So for the middle-aged, we could be either risky or safe depending on the income. So if the income is high, it's safe. If the income is low, it's risky. So for the classification, there are several methods. We are discussing just one of them today, which is decision trees, but we have other classification techniques such as, for example, we can use neural networks for classification, we can use k-nearest neighbors, Bayesian methods, and so on. So we will see that when we are building the decision trees from data, sometimes we can create more than one tree. So more than many decision trees may represent our data. And so there are many possibilities here. How can we choose the best one? So the optimal one, finding that optimal decision tree, is computationally expensive because we have an exponential search space because at each level of branching out in our tree, especially when the number of features is high, so we have several conditions to check. So it's going to exponentially grow, and therefore it is computationally expensive. But there are like several algorithms have been proposed so far that are suboptimal, not the best. They are suboptimal, but they can do it in a reasonable amount of time. So some of these algorithms that have been proposed, and most of them are based on the Hunt's algorithm, are, for example, ID3, proposed by Quinlan in 1986, and then it was further expanded to C45, and later CARD, almost at the same time as ID3, CARD means classification and regression. So that's why it's CARD. So it's classification and regression trees. Now, most of these algorithms we see today, they are mostly work like top-down and use a greedy approach. And we see what does that mean. So by top-down, I mean it starts from the root node from the top, going down. And by greedy approach, it means that at each node, at each stage, we just focus on finding the best attribute at that moment. So here is another example. We've seen this table before. So we want to see if, based on the weather condition, for example, if the weather is, what is the weather outlook, for example, or what is the temperature, whether it's windy or not. So based on these different features of the weather, we want to predict if that day is suitable for playing tennis or not. What is the class label here? What is the class label?
Whether we can play tennis or not.
Play tennis, right. So play tennis feature is a target variable or the class label, because that is what we want to predict. And we have several other attributes which we can use for condition, our test condition on the tree. So one of them is outlook, the other is temperature, humidity, wind, etc. Now, so this is just one representation of that data using a decision tree learning. There are several terms that you have to learn here. So we show the non-leaf nodes. So by the non-leaf node, I mean those nodes, those internal nodes, such as, for example, outlook, humidity, wind. And when I say leaf node, I mean that it doesn't have any trial, right? So the leaf nodes here are our class label, yes and no, that is playing tennis or not playing tennis. So those are the class labels. So we have internal nodes, outlook, humidity. We have terminal or leaf nodes, which are class labels. And we also have branches. And what are these values on the branches? For example, sunny, overcast, rainy. What do they represent? So if you look at the table, what does sunny, overcast, and rainy represent? So those are the attribute values, right, for the attribute outlook. So outlook attribute can be sunny, overcast, rainy. So these are the values. So they will go like our branches. So that's the branch. Or test outcome. Why test outcome? Because our tests are the features. For example, we can use the outlook feature as a test to see if, for example, based on how the outlook is, we want to decide whether we go to play tennis or not, right? So we want to test on that. So that's a test, which are our internal nodes. And then how we branch out them is based on their values. For example, if the outlook is sunny or if the outlook is rainy. So these are the distinct values of our features. And so a new case is classified by testing that case or that row against the nodes from root to a leaf node. So when we, for example, we have a tuple as the one I marked in blue, we get, for example, outlook sunny, temperature mild, humidity high, wind strong. What would be the predicted class label here? So we start, we said that it's a top down, so we start from the top. The outlook is sunny, so it goes to the left branch. And now the temperature is mild, which we don't have in our trees now. We have humidity. Humidity is high, so it again goes to the left branch after humidity. And so the answer is no. So if the weather outlook is sunny, but the humidity is high, it's not suitable for playing tennis. So here we can see another example of our training data set. Here we have several features such as age, income, student, credit rating, and the class label is buying a computer. So we want to see if a student is going to, if a person is going to buy a computer or not. So how do we do that? So we have some information for our customers based on their age, their income, whether they're a student or not, and how is their credit rating. Now, based on these features, we want to create a tree to predict whether a customer is buying a computer or not. Now, so here is just one example. So if you see here, like at this moment, you don't have to know how to select the root node. So you may, for example, ask, how do we know that here we should start with age? Why not, for example, starting with a student, right? So you may create several representations here. We talk about it, how to select it, the root node, and how to select it, the subsequent nodes later today. But just for now, I want you to know, for example, how it is, like overall how it works. For example, we see for the age, what are the values? So they're either less than 30 years, and this is actually, there is a small mistake here. It's not smaller or equal to 30. It should be smaller than 30. So this is how it should be. So smaller than 30 or between 30 and 40, and then greater than 30. So this is for the age. What could be the nodes of a tree here? So if you have this table, what could be the nodes in your tree? So if you want to build a tree from this data, what are the nodes here? The internal nodes. So when I show you the tree, it seems very simple, but if you want to think about it to create a tree from the data, there are are many possibilities. But let's say we are going to start with age. So the nodes that we can have, the internal nodes, which are our features, could be, for example, age, income, whether it is a student or not, and their credit rating. And if we are starting with, for example, age, and we had 3 branches for age here, right? What are the branches? Our test outcome. So this is the test. So we use our features as a test. So we use the age as a test here. And now, what are the branches? The feature values. So the age values. What are the categories of age here? We have less than 30 years old, between 30 to 40, and then greater than 40, right? And based on this age, so now look at the table for all the customers who are very young, like less than 30 years old. Are the class labels the same? Do we have the same class labels for all of them? Is it always no or is it always yes? No. So we have some customers whose age are less than 30 years old, and we can see the class label is no for them, like the first 2 rows. But we also have here some of the customers with age less than 30 years old that they buy computers, yes. So we have to check another condition, right? So if the age is less than 30 years old, can I have a leaf here and say, okay, the outcome is yes or no? Can it be a leaf? No, it can't. Why? When do we reach to the leaf? We reach to the leaf when all class labels, all our instances have the same class label. So for example, all the instances that have age less than 30, and here we have our class label by or not. So let's say we have less than 30 here, less than 30 here. So let's say, for example, we have 3 instances of less than 30. And here we have no, no, no. In this case, because all the instances of people who have less than 30 years old, they, like none of them buying a computer, and we have like the same class label for all of them, so we can say, okay, we reached the leaf. But that's not the case here. Some of them are yes, some of them are no, and it depends on other features. So we have to branch out our tree here. So now we continue branching based on other features. For example, can you say if age is less than 30 years old and let's say income is high, it's no. And if, for example, income is medium, is yes. Or should we go with the credit rating, or should we go, for example, with other features? So that's what you have to think. Now, here it tested with a student. Now let's go back to our table. Here we only have 4 features, right? And deciding to put which feature here after age is not easy. It wasn't even easy to think about which feature we want to choose for the node, for the root, right? So I could start with like a student. Or I could start with the credit rating. I could start with income. So deciding on which of these attributes go to our root node is something that we discussed today. We learn it later today. And so now let's say in this example we started with age, and this is the best attribute to start our tree. And we are branching, we are expanding our tree. So for less than 30 years old, again, we learn how to choose this one too, but we see that it is chosen as a student. Now, let's say, so what are the test outcomes? So here the test is whether a person is a student or not, right? What are the outcomes?
No or yes.
or our branches?
No or yes.
No or yes. So it's either student or not. And are we going to reach a leaf here? So for example, let's focus on this part. If age is less than 30 years old and a person is a student, so if age is less than 30 years old and a student is yes, so what would be the outcome?
Yes.
Yes. And is it always yes, or sometimes yes, sometimes no? For the age, for this condition, so age less than 30 and a student is yes. Okay, so it's always yes, right? So now we can say, okay, we reach a leaf because all our instances which satisfy our condition or satisfy our test, all of them have the same class label. So we don't have to further branch out our tree because we already know what would be the class label. So we can predict the class label. We can say that if age is less than 30 and the student is yes, so it will be buying the computer. And so we continue the same for the other branches. And so you see here, if age is, for example, between 30 years old and 40 years old, what would we have? What would happen? So if it's middle age between 30 and 40, sorry, I have to go back to. So the third row is yes, and then the next is yes, and then the next is yes, the next is yes. So all customers whose age are between 30 and 40 years old are buying a computer, are going to buy a computer. Because for all of them, our class label is yes. So that is when we reach a leaf. So again, we have a leaf here. And what if it's greater than 40 years old? So if it's greater than 40 years old, what condition would you choose? So for example, the fourth row, the age is greater than 40, and the outcome is the buy computer is yes, the class label is yes, the second one is yes, the next one is yes, and the last one is no. And again, it's not easy to find it like really fast now. We have like just a few features. You have to just see, for example, if age is greater than 40, if I'm going, for example, to choose, so you either have to choose income here or a student or credit rating, right? So you have to see with which one you reach to the same class level for all the instances. And that's why we're using the decision tree algorithms, because that's not easy for us to like. That's why it's expensive. It's computationally expensive. It's not easy to just, let's say we have hundreds of features here. How can we like go with all these combinations? But just for now, we, for example, use the credit rating. So we have a credit rating here. So if the person is, if the age is greater than 40, what are the values of credit rating? So what are our tests or branches of credit rating? So the values, the branches shows the value of that attribute. Now for the credit rating, we have fair and excellent, right? So those are the values for the credit rating. So our branches are either fair or excellent. Now, if the age is greater than 40 years old and the credit rating is excellent, what would be the result? So if age is greater than 40 and credit rating is excellent, it's no. And credit excellent, then no. Now, we reach a credit rating excellent. Why did we reach it here? Why didn't we branch out more? So we said, okay, if age is greater than 40 years old and credit rating is excellent, why we don't use another test here, for example, and whether it's a student or not, or whether the income is high or medium. Because for all the rows that age is greater than 40 years old and the credit rating is excellent, all of them, the class label is the same. For all of them is, for example, no. So we don't need to further classify, because what is the role of classifier? We want to like predict and classify to see whether classify our input to see whether a customer, for example, buy or not buy. So if we reach to the point that we see all of the instances are satisfying this condition and they're all going to buy, or for example, not buy, if all of them have the same, so there's no point of like going further. So now you, so far, I would like you to understand what is a decision tree, how we build decision tree from our data. In this case, our data was represented with a table of, for example, customers, whether they buy computers or not. And we don't know, I don't expect you to know how to select the features at each level of our trees, right? We don't know how we choose age as a root node. We don't know why we choose a student here and not, for example, credit rating here. We don't know why we choose credit rating here and not, for example, other features. So this is what we are learning now, how to select those root node or other features. So as I mentioned, most of the algorithms that have been proposed, I said there are many different ways of representing a decision tree. Many algorithms have been proposed. And among them, the ones that we are discussing today, most of them are using the top-down approach. They start from the root node. And they use a greedy or like divide and conquer approach, which means at each stage, we select the best feature at that moment. And so, for example, back to our example of whether we want to predict whether a day is suitable to play tennis or not. So you all have that example. And we want to decide, so we see, for example, in that example, we started from the outlook as a feature. We could start from temperature, we could start from humidity, wind, etc. Now, which rows here have the outlook sunny? So what attributes do we have here? We have outlook, and we have temperature, humidity, wind, and plane tennis. So if the root node is outlook, what could be the branches? So the outlook values, the branches represent the values of that attribute. So what are the values? They could be either sunny, rainy, or overcast. So these would be our branches. Now let's say it's sunny. So in this example, you will see it better because we have, we can use D1, D2, like the days, to show, for example, how many instances we have for each division. So now in this partition, if the output is sunny, which day satisfy that? So D1, D2, what else? Yep, D8, D9, and D11. So it's D1, D2, D8 or D8. And then for the overcast, we have D3, D7, 12, and 13. And then again for the rainy, we write which days we have. Now, if the outlook is sunny and humidity is high, which rows satisfy this condition? D1, D2, D8. So now just I want you to see what I wrote here. D1 minus, D2 minus, D8 minus. By minus, I mean the predicted is no. Like, so because we are playing tennis, either yes or no. If it's yes, I mark it with plus. If it's no, I mark it with minus. Now, so if the outlook is sunny and the humidity is high, and then all class labels are no, and which rows satisfy that? D1, D2, D8. And if the humidity is normal, then it's suitable for playing tennis. The outcome, the class label is yes. And which rows satisfy that? D9 and D11, right? So we continue the same for all other features and branches. So now the main issues, the main design issues in decision tree, as you have, if you were thinking with me from the beginning of this lecture about how to create the decision tree based on the data that we have. So what were the issues here? So you want to, like, you have that table, you want to design a decision tree. What are the problems? What difficulties you have when you want to, like, if I show you a tree, it's very easy to follow a line. But what is the challenge here? Yep, how to choose our root node. How do we know that we have to start from the outlook and not humidity, or not, for example, wind? So that's one of the issues. Or, for example, another issue is when should we terminate our branching? So how far we should continue? So these are the main issues: how to select an attribute for a node, when to declare a node terminal, and how to assign a class to a leaf node. So assigning a class to a leaf node is based on the majority voting. So the majority of, we look at the instances, let's say most of them belong to, for example, class label yes, and then we choose yes. So that's based on the majority voting. So the way that we select an attribute for a node, you may also hear a splitting criterion. A splitting criterion help you. There are several techniques and formula to do that, but that is actually what helps you to choose the right feature. When should you declare a node terminal, and what is our stopping criterion? That is when we reach a leaf. Do you remember when in that example we were trying to design a decision tree, and at some point we reached a leaf? So how did we know that we reach a leaf? So for example, if the outlook is overcast, why did we reach a leaf here in this example? Because for all instances in the table, in our data, that the outlook is overcast, the class label is the same. So whenever the outlook is overcast, it's always suitable for playing tennis. So always the class label is the yes. So why do we need to go further, right? because now we have a rule. If Outlook is overcast, then the class label is yes. So we don't have to classify further. And we want to see how to select an attribute. So, or for example, what attribute is best given a set of features that we have in our table and set of examples. For example, we show two examples here, attribute 1 and attribute 2, and different, like using different features as a root node. There are many selection criteria. One of them is information gain, the other is gain ratio, Gini index, chi-square, and several other methods. What we'll discuss in this class are the first three ones. So these are the techniques that are used to select the best feature, or your root node and the subsequent nodes. What would be an ideal split? Let's say, for example, here we have, for example, in an original data set, let's say 29 examples or 29 instances of our data belong to class label yes, and 35 instances belong to class no. So what would be the ideal split? So just a hint, what would be the ideal split? It's a split that helps you to reach a leaf, right? A split that your partitions are all pure. That is, they all belong to the same class label. So if you have two class labels, for example, yes and no, you want to partition in a way that all instances, for example, in one branch, all are representing yes, and the others are no. So the ideal split would be something like this, right? Why is it an ideal split here? Because we have no instances belonging to class no on the left child, right? So all the 29 instances that belong to class yes, they all divided into that partition, and we call it that it's pure. It helps you to understand also the concept of entropy that we learn how to calculate it today. So the attribute with the highest information gain is selected as a root node for a splitting criterion. We will learn how to calculate the information gain using the entropy, which I will let you know what that means. But for now, I just want you to understand that the ideal split is the one that in each of our branches outcome, we reach a node that is pure. Like for example, here, if we have 29 instances of class yes, on the left child we have all class yes, and on the right child we have all class no. So there's no impurity here. And we call a partition as pure if all the tuples or all the instances belong to the same class label. That's when we wanted to design our decision trees. We said, okay, we reached to the leaf node. So what is entropy? You can think of entropy as a measure of like impurity, and it's a measure commonly used in information theory that characterizes the impurity of an arbitrary collection of examples. And we said that by pure, we mean that all instances belong to the same class label. That is the purity. Now, how do we calculate that? So let's say we have a set S. That is our data set. For example, we have B1 to B7 in that example of the predicting the day to see if it is suitable for playing tennis or not. So we had, for example, B1, B2, day 3 to day 14, right? So we had 14 days. So that was our set. And K classes, C1 to CK. In that case, how many classes did we have? We had two classes, whether playing tennis or not. The entropy of S with respect to the k classes is defined as, so we have minus sum of PCI multiplied by log of PCI. So what is the PCI? Is the probability that that instance or that example belonging to a specific class. For example, back to our example, we want to see if it belongs to the class playing tennis or not, for example. So now if all the examples in S in our data, if all of the examples belong to the same class, which means the S is pure, right? So if they all belong to the same class, for example, we have a table, we see if outlook is overcast, it's always playing tennis is yes, right? So for all of the instances that the outlook is overcast, what is the class label? Yes, so it's the same. So that means that the S is pure. So if all examples in S belong to the same class, then the entropy of S is 0. Why? So you can calculate it using the formula. So we have, I wrote it here, so we have entropy as minus sigma to our class of probability of our examples belonging to that class, and we multiply it by the log of PCI. Now we want to see what is if all the instances belong to the same class. The entropy is 0. Why? What is the probability of instances belonging to, for example, that one class? If all instances belong to the same class, what would be the PCI? So in that example, let's say we have, in the example of the outlook, the weather to predict whether a day is suitable for playing tennis or not. How many classes did we have? 2, right? So we had like the class labels were either no or yes. So we had 2. So the probability of class 1 and class 2, what is that? When all classes belong to the same class, let's say we have 10 instances and all of them belong to the same class, so it's 1. So it's 100%. It's 1. Sorry. And why the entropy is 0 then? So if this is 1, because this is 0, right? 2 to the power of what? So that is 0. Because 2 to the power of 0 is 1. So because the log is 1, the result of the log of PCI is 0. And so the entropy of S is 0. Now, if half of the examples in S belong to class 1 and half of them belong to class 2, what would be the entropy? Why is it 1? So what is the probability that an instance belongs to class 1? If half of the classes, let's say we have 10 classes, half of them, 5 of them belong to class 1, 5 of them belong to class 2. What is the probability that an instance belongs to class 1? 50%, right? So you have, it's 50, half. So 1. So the probability here is this. And so this is for class 1, PC1, multiplied by log of this, right? And you have the same for the second class, which is, again, so now, how do you calculate this? So what is log? What is this? 2 to the power of what number is going to be? How do you represent this? -1, right? 2 to the power of -1. So it will be 1/2. So the entropy of S here is 1 because we have, using that formula, you see that the result is going to be 1. Now, let's say we have 9 examples in class 1 and 5 examples in class 2. So if we have if we have 9 examples in class 1 and 5 in C2, then what is PC1? What is the probability of an example being in class 1? So in total, we have 14 instances, right? 9 and 5 is 14. What is the probability that it goes into class 1? It's 9/14, right? And what is the probability of examples to be in class 2? PC2 is 5/14. And then using that formula for entropy, you can calculate the entropy here. And using this entropy, we will also use another formula to calculate the information gain. And the way that we select the root node or the root feature is the feature with the highest information gain. So for that, we have to first learn how to calculate entropy. So another example, for example, if examples are uniformly distributed in 3 classes, entropy of S, again, is calculated using the same formula. So now how to calculate the information gain? So we talked about the attribute selection criterion, right? And we said that attribute selection criterion can use different techniques, such as information gain, to choose the best attribute to split a data set. For example, that helps us to decide whether we choose outlook, temperature, wind, or other features as a root node. So what is the formula for the information gain? For a gain of S with respect to A is our feature. For example, we can have the gain S and feature outlook. We can have S and feature A wind or temperature or other features. You have to first you have to calculate the entropy of that subset or that partition. For example, if the outlook is sunny, you calculate the entropy of that, and then you deduct it from the entropy of S, the whole data set. Because you want to see how selecting that partition, for example, partition of outlook sunny, how does that affected your learning, right? So now, if our feature is outlook, so we say that using a feature a data set is split into S1 to Sm. What does M represent here? The number of values, distinct values of each feature, right? For example, if the outlook is sunny, what would be the M? Sorry, for the attribute outlook, what would be the M? Number of values, right? So we can go to S1, S sunny, S2, S overcast, and S rain is S rainy. So these are our partitions, subset of our data, right? So we have a data, for example, when the outlook is sunny, we have 5 instances here. If the outlook is overcast, we have 4 instances here. And if the outlook is rainy, we have some instances here. But the M is the number of distinct values that the selected attribute has. For example, if the attribute is temperature, so look back to our example. So if the outlook is temperature, what is M? Against 3, because it's either hot or mild or cool, right? So we have 3 values. And the same for other features. Now, okay, so we also know how to calculate the information gain or gain of S with respect to attribute A. So this is our feature is equal to entropy of S, which we calculated here, minus I from 1 to m, and n is the number of distinct values that a feature has. And then here we have to choose the entropy, we have to calculate entropy of SI. For example, entropy of the outlook or other features. So that's our feature. Now, why do we have here SI over S? And these two reflect the number of examples in set S and number of examples in set SI. For example, number of examples in the original data set and number of examples in one of the subsets. So it's kind of normalizing, right? So you can think of it as the weight of that partition. So now let's see this with an example. We want to calculate the entropy and calculate the information gain for all the features that we have in a table so that we can decide which feature goes to the root node. So what are the candidate features here to select as a root node? So we have outlook, temperature, humidity, and wind, right? So we can start from either of these 4 right? So we can start from outlook. We can start from temperature. We can start from wind or humidity. Now, deciding when we have that data and we want to design a decision tree, so the first problem is which one should be the root node, right? In order to find that, we need to, for each of these features that we have, our candidate attributes, for each of them, we calculate the information gain. And to calculate information gain, we need to calculate the entropy. The one with the highest information gain is the one that is less pure and need more branching, so we choose it as a root node. If the entropy was 0, it means that it's already reached to the leaf, right? So it's not suitable for being in the root node because it's a top-down approach. We're starting from top and branching out to bottom. So we want to choose something on the top as a root node that has the most impurity or higher information gain. Now, so I'm going to calculate just for one of them, and at home you can calculate the entropy and information gain for all other features. Now let's do one of them as an example together. So for example, we have humidity, and what was the original set? So our S here, what does that 9 plus 5 minus mean? We have 14 day in our data, right? We had D1 to D14. And if you go back to this data, how many of them are no, how many are yes? So you look at the class labels, 5 of them are no, 9 of them are yes. So this number represents that. So S plus 9 and, or sorry, 9 plus 5 minus means that. So we have 9 class label yes, 5 class label no. And how to calculate the entropy? We already calculated the entropy for this one. Do you remember in the slide, if you go to the slide of entropy, we said one of the examples was if 9 examples belong to one class and 5 examples belong to another class, right? And the entropy would be, what would be the probability of belonging to class 1? 9 to 14, right? Multiplied by log of 914 minus 514 into log of 514, right? And this number was 0.940. So this was the entropy of S, right? Do you have any question here? Is it clear? Okay. So now for humidity, we have 2 outcomes. What are the test outcomes here? Either its humidity is high or normal. So if the humidity is high, so now for the humidity high, we want to calculate S high. What would be the number here? What does it? It's the SI in that example. Do you remember that I said it's a partition or a subset of our data? Now that subset refers to those days that humidity is high. So let's see which days humidity is high in total. I'm not going back to that table, just you check it in your slide. So in that slide, 7 days humidity is high. Now, in those days, in those 7 days that the humidity is high, 3 of them belong to class label yes, which means that in 3 of those 7 days, the day was suitable for playing tennis. In 4 of them was not suitable, so that's it. And again, you calculate the entropy for S high. You use that formula to calculate the entropy. You calculate the probability that an example belongs to class. What is the class here? Class of, for example, humidity high. So entropy is, so we have 3 class label yes, 4 class label no, and then we have entropy of S high. Here we had entropy of S. Now this number is 0.985. And then we did the same for humidity normal. So in our table, we have 14 days, 7 with humidity high, 7 with humidity normal. Now, among those with humidity normal, among those 7 instances with humidity normal, 6 of them have class label yes, 1 of them have class label no, right? So it's 6 plus, 1 minus, and the entropy is calculated as what? For those 2 classes, we calculate the probability. So PC, for example, 1 and PC2, and then calculate entropy using that formula. We have this number 0.592 of S normal is 0.5 something, and here S of normal is 6 plus 1 minus. Now, so far we calculated the entropy for humidity. We can also calculate the information gain, which we show with gain S with respect to attribute A, which is humidity here, using the formula again. So how did we calculate that gain S and humidity? So first, when you want to calculate gain of S and humidity, you have to calculate the entropy for humidity, right? So what was the entropy for S, which was 0.940 minus. Now you have the number of examples in I and number of examples in S, which is 7 to 14 and 7 to 14, because for both classes of humidity, either high or normal, we had 7 instances. So it could be like it's accidentally the same here, but it could be different. So we have 714 here and 714 here. And then those numbers that we multiply 714 are the entropy of each subset, right? So we have the entropy of S high, which is this number, and the entropy of S normal, which is 0.5. So the way it works is that you first calculate the entropy for each feature, for example here for humidity, and then based on whether it's high or normal, again you calculate the entropies and the information gain, right? The information gain is based on all those entropies. Now, what is the information gain for humidity? 0.151, right? So I provided the numbers here. Now, 0.940 is the entropy of S, and the other two numbers are entropy of S for humidity high and humidity normal. Now we have to repeat the same process for all other features. For example, for the outlook, we have to calculate the entropy for the outlook sunny, for the outlook overcast, and for the outlook rainy, right? So among all 14 days that we have in a table, 5 days are sunny, right? And among that 5 days that the weather is sunny, how many of them belong to class label yes? 2. So we have 2 plus. And 3 days, 3 of those 5 sunny days belong to class label no. So we have 3 minus. We calculate the entropy using the formula that we have here. So we know the probability of examples being in each class. So for example, being in class yes or no. And based on the entropy of each of these outlooks, for outlook sunny, outlook overcast, and outlook rainy, now that we have entropy of each of these, we can now calculate the information gain, which is based on the formula here. So now I repeat the same calculation for all 4 features that we have here, and I'm selecting the outlook Y. So we selected outlook to be as the root node. What is the reason? Because it has the highest information gain. Now, okay, so far we reached to this point. So we have the outlook as the root node. Now we want to decide how to choose the rest of the features. So here, for the outlook of overcast, we already reached to the leaf. Why? Yeah, why is it pure? Yeah, because all examples, all instances of outlook overcast belong to the same class, right? So the entropy is 0. So we said if all examples, all instances belong to the same class, the entropy is 0. And so because entropy is 0, so we reach to the leaf. And for the other ones, how about the other ones? For example, for the outlook sunny, what feature should I choose there? So again, in order to test what attribute to be selected here, we have to do exactly same procedures. So we started from the main set there, calculated the entropy, and then for each of these outcomes that we had, we again calculated the entropy for each of them. Now we do the same here. So we start from, for example, outlook sunny, and we calculate the information gain for, now, just be careful here, S is S sunny here. So now because we are in the subset of S sunny, right? So when we want to choose this, so we know, for example, we are starting from here, overcast, rainy, sunny. So when we are here, in order to choose this attribute, in order to choose this one, we have to calculate the information gain for each of these different features that we can have here. For example, here we can have, what other features do we have except the outlook? We have humidity, we have wind, or temperature. Now, so here, this could be either humidity, it could be wind, or it could be temperature. So to choose which attribute comes after outlook sunny, to choose this, we have to find the information gain of S sunny, which are a subset of the data that are sunny, with all these features. One time with humidity, another time with temperature, another time with wind. Now we choose humidity here for the outlook sunny to branch out further. Why did we choose the humidity? Because the information gain that we calculated for S sunny, for the subset of data that are those days that are sunny, with respect to the humidity feature. So that's the greatest information gain. So we choose humidity here. What about this one? The same procedure. So we have to calculate the information gain for the outlook rainy, right? For S rainy. So gain S rainy, and the same features, right? We can have humidity, we can have wind, temperature, etc. And after we chose entropy, after we chose humidity, so humidity has, how many branches do we have in humidity? 2 branches, right? It could be either high or could be normal. So if the outlook is sunny and the humidity is high, what are the class labels for the outlook sunny and humidity high? How many class labels do we have in yes? How many class do we have in no? So for humidity high, they all belong to no class, right? So we reach to the leaf because all of them belong to the same class label. All of them belong to none. Also for humidity normal, all belong to class label yes. So we reach to the leaf. And we repeat the same process for the wind. Wind can be strong or weak. For those days that are rainy and the wind is strong, all of them belong to class label no, so we reach to the leaf. And for those days that are rainy and wind is weak, the class label is yes. So for next lecture, I'm going to further a little bit talk about gain ratio and Gini index, and we will also talk about pruning decision trees. We will definitely have a hands-on session on pre-processing and decision trees together, because your assignment 1, which I'm going to announce it in a few days, your assignment 1 is contains both data pre-processing and decision tree. Do you have any questions? No? Okay, thank you.